Hello, and welcome to the Prelab video for Experiment 3 on chemical kinetics. In this lab, we're going to be looking at the rate of a particular chemical reaction. So chemical kinetics is all about speed, the speed at which chemical reactions happen. And chemical kinetics is a very important thing because the speed of a reaction really matters a lot. So thermodynamics, which you've learned about, tells us about whether a reaction can happen and tells us about equilibrium and things like that. Kinetics tells us how quickly it'll happen. As a dramatic example of this, for example, carbon in the graphite form is thermodynamically the lowest energy form of carbon at room temperature and atmospheric pressure. But we can also have carbon in lots of other forms, such as a diamond. And carbon in the graphite form versus the diamond form should go to graphite, according to the Gibbs free energy. But the speed of this reaction is very, very slow because of, there are lots of chemical bonds you have to break in a diamond to get it to turn into graphite. So, even though this is favored to go from diamond to graphite, it is so slow that we can say diamonds are forever, even though thermodynamically they're not the most favorable form of carbon. Some other examples, one example that's mentioned in the lab write-up is iron rusting, right? Iron plus oxygen going to iron oxide. I may have the stoichiometry wrong here. But, right, this is a relatively slow reaction, whereas, things like an explosion, something like hydrogen plus oxygen, forming water, is a very fast reaction and is used in rockets to, send rockets to space. So speeds of reaction are really important, and chemical kinetics is all about measuring that quantitatively. So there are many different things that affect rates of chemical reactions. Some of the things the main thing that we'll be altering in this lab is the concentration. So the concentrations of reactants in particular are one of the main things that drive the speed of chemical reaction. The other major things that affect chemical reactions, the speed, is the nature of those reactants. What type of things are you reacting? How energetic are they? How easy, reactive are they? Temperature is another important variable that controls speed of chemical reactions. That's not something we're going to change in this particular lab. And the final thing is a catalyst. Catalyst is a way to speed up a chemical reaction. And these are very important in chemistry, and lots of people study how to make better catalysts. And our biological chemistry relies a lot on catalysts known as enzymes inside of our body to speed up chemical reactions. So for this particular lab, what we are interested in studying about the rate of a chemical reaction is what's known as the rate law. So before we can talk about a rate law, though, we need to talk about what is a reaction rate. So a reaction rate is the change in the concentration of a reactant or product over a certain amount of time. And this is often written as delta meaning a change. And say, we're looking at reactant A over, how long it takes for that concentration to change. So this is, so for this example, this would be, let me give a specific reaction here. Let's say we have A plus B going to C plus D. As physical chemists, this is our favorite chemical reaction, just a generic reaction. Right, and so this would be the change in concentration A. This would be a negative value, because we lose A. We could also write this as C or D appearing, right? So the change in the concentration of C over the change in time, this would be a positive value because we are increasing the concentration of C as the reaction goes along. Now, the rate of the chemical reaction is either, are these changes in concentration, and we can write that reaction rate in a rate law. And the rate is equal to a rate constant that we call K, multiplied by the concentrations of the reactants. So in our case, this would be A and B, but these A and B may be raised to some exponents we'll call X and Y. And the goal of this experiment is we want to measure what is the rate law for a particular reaction. The reaction that we are going to be considering in this lab is S2O8 persulfate, 2-, reacting with iodide ions. So all this is an aqueous solution going to I2 plus sulfate, 2 sulfate ions. Right, so this is the reaction we're interested in measuring. And so our A and B here are going to be the persulfate concentration and iodide concentration. And just looking at a reaction, though, we don't know what the values of X and Y are going to be offhand. There's no way to know without doing an experiment. Even if you look at the stoichiometry of a reaction, it does not tell you what these exponents are going to be. It's something you have to determine experimentally. And that's the purpose of our lab today, is to measure the rate of this reaction, find the rate law, find the rate constant for this reaction, so that we can quantitatively talk about the rate of the reaction. So let's look at the order of the reaction. So the reaction order is related to these exponents. So for example, if X was equal to 2, for example, that would mean that our reaction is what we call second order in A, meaning that if the concentration of A matters to the power of 2. So if we say have double the concentration of A in our reaction, the rate will increase 4 times because we have 2 squared. We can also have different values, right? So maybe Y is equal to 1. We would call that first order. And then we have for this particular reaction, it would be first order in B, because Y is the exponent that goes with B here. So there, if we multiply the concentration of B times 2, the rate would still increase, but now only 2 times, because that squared is no longer there, right? And so the behavior for a second order versus a first order reaction is different because of that exponent that's present. It's possible to have 0 order reactions, so it's something that doesn't depend on a concentration of a particular reactant. Third order reactions, not so much. But in our case, generally these exponents, these orders, are going to be integers. So they're going to be 1 or 2, something like that. And we could say this reaction overall, if X was 2 and Y was 1, the overall order would be third order, because we just add together the orders of each of the reactants in this case. To measure the rate of chemical reaction, we have to be able to keep track of the concentration. And for the reaction that we're looking at, again, just as a reminder, that's S2O8, 2-, reacting with iodide to go to I2 plus 2 sulfate ions. There's nothing in this that we can easily keep track of. One way to commonly keep track of concentrations of chemicals is to look for something that's colored, and none of these species have color by themselves. So what we do is, in this reaction, we couple this with a second reaction. We couple this with the reaction of I2, so our product here is a reactant in the second reaction, plus thiosulfate, that's this polyatomic ion, S2O3 2-, will react to give us back iodide and form S4O6 2-. Now, the thing that's useful here is that this iodide gets used up the iodine gets used up and the iodide is regenerated. So we keep the same constant concentration of iodide, but our thiosulfate that we add reacts with our iodide and uses it up. So our product is basically not going to be present because it'll react with the thiosulfate. What we're going to look for in this lab is the combination of iodine plus starch makes a blue complex. So in all of our reactions, we're going to add a small amount of starch to the reaction. And that starch will complex with the iodide that's formed and form a blue color. And when that blue color is formed, we know that however much thiosulfate we added got used up. So, that's the idea behind the actual experimental procedure we're going to do here. We're going to make separate solutions of persulfate and iodide, mix them together in combination with thiosulfate, and look for when that thiosulfate gets used up. When we know the number of moles of thiosulfate we put in, because we know the concentration that we made and the amount of it that we put in. When that thiosulfate, that number of moles is all used up, we'll see the blue color. And then what we'll do is we'll add additional thiosulfate. Same amount that we had in the reaction to start with. And the color will disappear because, again, the iodine, the I2, will react with the thiosulfate, and we will lose that I2 starch complex. And then we wait for it to wait for the blue color to show up again, and we repeat this a few times, as outlined in the experimental procedure. So that is the idea of how we're going to keep track of this reaction. We have a second reaction, this clock reaction, that is using up our iodine. And I will show you an example of this that'll come just after this, of doing this in the lab and what this actually looks like. This is a remote lab, so you won't actually be performing this experiment. So I want to show you, what this looks like when we do it in the lab. And again, what we're going to measure is a time. That's what we really care about in a kinetics experiment, is how long does it take for a reaction to happen. So you use a stopwatch or your phone, whatever, and you time from when you mix these things together, when does that blue color appear? You write down that time, and that's what's given to you in your lab write-up. And then we add more thiosulfate, wait for the blue color to appear again, write down that time, and repeat this several times to give us an idea of the rate of the reaction. How long does it take for this number of moles of thiosulfate to get used up, which is really what we're after. Is the rate that we care about is the change in the concentration of this persulfate over time. And we're using the thiosulfate as a proxy for this.
Hello. I'm going to show you what this experiment looks like now. I have to lean over to say hi because I got the webcam pointed down so you can actually see the reactions going on. So what we have here is an Erlenmeyer flask and beaker. These are our two parts of our reaction. So this is mixture 1, and so this is according to experiment 2 in the lab write-up. And so this is the first part and the second part that we're going to mix together. And then back here we have sodium thiosulfate that we're going to be adding as a way to keep track of the reaction. So let me explain what's in the beakers when we mix them together and watch the reaction happen. So this Erlenmeyer flask here, this has our potassium iodide, one of our reactants, as well as a small amount of EDTA to complex any metal ions that are present. Potassium nitrate makes up the bulk of the rest of it, solution, and that's to keep the concentrations of ions roughly the same between different experiments. And then there's a small amount of starch as well, and the starch is present to complex with the iodine so that we can see the color when the reaction, when all the thiosulfate is used up. So, and there's the thiosulfate, 1 milliliter of the 0.4 molar thiosulfate in here, and that's what's going to get consumed, and that's our clock reaction, that when the thiosulfate is gone, we'll know the reaction is done because it will change color. In this solution, this is just the disulfate, the proxy disulfate, or S2O82 minus reactant as well. Then back here I have a small beaker that has a little bit of thiosulfate in it. And what I'm gonna be doing is when the color appears, I'll add more of this, which will make the color disappear because it'll react with the iodine that's been formed. And this is to show you, if you did this in the lab, we would do this multiple times and measure the time difference between each of these. So let's go ahead and mix these together. The reaction should take around a minute or maybe a little bit longer. So mix these together, swirl this around. I'll move this up here so you can see it. We have a clear solution right now, so nothing's happening. All right, so, and that is because what's happening is our reaction is happening. We have iodide and persulfate reacting and forming iodine, but the iodine is immediately reacting with the thiosulfate and turning back into iodide. And so we don't see that product of the iodine and starch complex until all of the thiosulfate is gone. So nothing too exciting yet. This one isn't exciting until the reaction is done and we see the color change. And I did test this beforehand, so I know it will work. When I came in, the solutions were not fresh, and so I had to make them up fresh again, and then the reaction worked. It didn't work when they were not fresh. All right, still no color change, still looking clear. All right, and now hopefully you can see it turn dark. And now if I add 1 milliliter of the thiosulfate and mix it around, you can see that the color disappears. And if we wait about the same length of time as we waited the first time, we should see the color change again. So it may be kind of hard to see. Let me try and get this in better focus, but you can see the solution has gone clear again because I added more thiosulfate. We'll just go until this is done for a second time. We won't do it, repeat it the number of times you would in lab. In lab you would do this 5 times, but we're just going to do it twice. But you have all the data from experiments where it was done multiple times. And again, the goal of this is to see how long does it take to use up the thiosulfate, because that tells us how fast the persulfate and iodide react. The nice part about that second reaction, the thiosulfate and iodine, is that it's a very fast reaction. So what we're limited by is our reaction that we actually care about, the persulfate and iodide reaction. And there we go, color changed again. So you would repeat that more times, but that is how the experiment would look.
Now that you've seen an example of what the reaction looks like in action, even though you won't have the chance to do this in lab for this particular year because of COVID, I wanted to show you how to approach graphing your data in Excel. So I've got an empty workbook open here, well, almost empty. And I'm just going to do an example of one set of data. You'll be doing this for 3 sets of data at the same time, but I'll show you how to do it with one. You can basically copy a very similar process using the outline that's in the lab write-up to do the other sets. So your first column will be experiment 1. And you'll need to put the cumulative times for the reactions there. So start with 0, and I've got some dummy data here that I came up with on my own. This is not real data, but will give us something that we can work with. So don't use these numbers is what I'm saying. Look at the numbers that are actually in your lab write-up. Okay, so these are cumulative times. You can see they keep increasing. They're not about all the same, which is what you should see for your not cumulative times for the time between each one. You need to add them together to get these cumulative times. And then we need the number of moles reacted. Well, to start with, there was 0. And as shown in your lab write-up, as we keep going, we've been adding additional thiosulfate, which corresponds to an amount of persulfate that reacted that is equal to 2 times 10 to the minus 4 moles for every aliquot. So each of these points will just be 2 times 10 to the minus 4 bigger than the point before it. Okay, so that is what our data would look like. And if you were doing this for your experiment, you would have an additional set. Experiment 2 would go here, and experiment 3 would go here, and you would have your cumulative times that would go here. Okay, but for now, we're just going to worry about our first set of data, this set of data. So we select the data here, we hit Insert, click here. We want a scatter chart that does not have any lines connecting the points. So we should get something that looks like this. I always like to get rid of a chart title. The one thing you'll want to check and make sure is that your y-axis is the moles and your x-axis is the time. So this should range from 0 up to 1 times 10 to the minus 3, which it does, and this should range from 0 up to, you know, a few hundred seconds, which it does on the x-axis. So you want to make sure that those aren't swapped. You want to make sure that those are correct. Now, the thing we need is we need to know what's the slope of the best line that goes through this. And the way we're going to do this is we're going to go up here to Add Chart Element, click on this, hit Trend Line, and go to More Trend Line Options, because we need to change some of the default settings here. Okay, so we want to make sure you're in this thing that looks like a bar chart. We want a linear trend line, and scroll down. We want to display the equation on the chart and display the r² value on the chart. Okay, so now we can see our trend line here. This is the slope. This is the r² value. We want to see an r² value that's close to 1 if our data looks good. But we only have 2 times 10 to the minus 6. We need more significant figures than that. So what we do is we double click on this, and we click here, and we need to change the formatting of the numbers in here. So we can change this. We need to change this to scientific and 4 decimal places. And now we can see our trend line is formatted properly. So we can see that our slope is, in this example, 2.0836 times 10 to the minus 6. That's what this E minus 0.6 means. It means times 10 to the minus 6. This is the way in Excel that scientific notation is written, just like I did over here with the number of moles. And you're going to have 3 different trend lines on here, so you'll need to label these. So we'll call this one Y1, and you can just put your cursor in there and change that. And you can add a 2 and a 3 to your other plots. So that's a quick rundown of how you can get the information you need from Excel, so including the slope and the slope of the trend line, which is the most important thing you need to get from this. And one thing to note is that the slope is in units of moles per time. The rate that we want to measure is a concentration per time. So there's a conversion factor you're going to need to take into account there for your experiment.